On November 9th, 2025, images of 3I Atlas revealed something that should be physically impossible. The object was ejecting material at a rate that would require a surface area 16 times larger than what the Hubble Space Telescope actually measured. Think about that for a moment. We're not talking about a minor discrepancy or measurement error. We're talking about an object that would need to be fundamentally different from what our most advanced orbital observatory saw just months earlier. How is that even possible? Right now, astronomers are staring at data that doesn't make sense. The calculations have been checked and rechecked. The observations have been verified by multiple independent sources, and yet the numbers refuse to cooperate with what we know about how comets behave. This isn't speculation or sensationalism. This is Harvard astrophysicist Avi Loeb walking through mathematics and arriving at a conclusion that challenges everything we thought we understood about this object. But before we dive deeper into what those November images revealed, I need you to do something for me. Hit that like button and drop a comment telling me your coordinates. Where are you tracking 3I Atlas from? Northern Hemisphere? Southern skies? Are you watching from a backyard telescope, following online data, or just fascinated by the mystery unfolding above us? Let's map our global observation network, because what we're witnessing right now isn't just another comet passing through our solar system. This is a real-time scientific investigation where the evidence keeps piling up in ways that nobody predicted. Let me take you back to July 21st, 2025. The Hubble Space Telescope captured detailed images of 3I Atlas as it approached the inner solar system. Using those observations, astronomers calculated the object's maximum diameter at approximately 5.6 kilometers. That measurement wasn't a rough estimate. Hubble doesn't guess. It provides precise photometric data that allows scientists to determine the size of distant objects with remarkable accuracy. So we had a baseline. We knew the physical dimensions of what we were dealing with. A comet roughly 5.5 kilometers across, consistent with what you'd expect from a typical interstellar visitor making its way toward the Sun. Fast forward to November 9th, 2025. Post-perihelion images started coming in. Perihelion, for those unfamiliar with the term, is the point in an orbit where an object comes closest to the Sun. For 3I Atlas, that moment arrived on October 30th. And when astronomers captured images in the days following that closest approach, they saw something extraordinary. Massive jet structures extending millions of kilometers in multiple directions. These weren't the modest dust tails you see in textbook photos of comets. These were colossal plumes of material being expelled from the object at a scale that immediately raised questions. Avi Loeb sat down with this data and started calculating. He's not someone prone to wild speculation. His approach is methodical, grounded in peer-reviewed physics and published research. He wanted to understand exactly how much mass 3I Atlas would need to lose in order to create the jet structures visible in those November images. The calculations weren't simple, but they were straightforward. You take the density of the material in those jets, the volume they occupy, the velocity at which they're moving, and you work backward to determine how much mass the object must have expelled over a given time period. The numbers told a clear story. To produce the observed mass loss, 3I Atlas would need a radiating surface area of at least 1,600 square kilometers. That's the area required to absorb enough solar energy to sublimate the amount of material visible in the jets. When you calculate the diameter of a sphere with that surface area, you get roughly 23 kilometers. Now let's pause there. A 23-kilometer diameter object. But Hubble measured a maximum diameter of 5.6 kilometers. Do you see the problem? The surface area required to generate the observed mass loss is 16 times larger than what the object actually appears to be. This isn't a case of one measurement being slightly off. This is a fundamental mismatch between physical reality and mathematical necessity. If 3I Atlas is what we think it is, a natural comet composed of ice and rock, then it should follow predictable rules. Solar radiation heats the surface, volatiles sublimate, gas and dust get expelled. The relationship between surface area, absorbed energy, and mass loss is well understood. We've studied dozens of comets. We know how they behave. And yet, 3I Atlas is defying those expectations in a way that suggests something more complex is happening. Loeb's analysis didn't stop there. He cross-referenced the surface area calculations with earlier observations. In August, the James Webb Space Telescope had captured spectroscopic data showing that 3I Atlas was composed primarily of carbon dioxide, about 87% CO2. That's important because different materials require different amounts of energy to sublimate. Water ice, for example, needs significantly more energy per gram than carbon dioxide. So if we know the composition, and we know the solar flux at perihelion, we can calculate exactly how much surface area should be sublimating to produce a given mass loss rate. And once again, the numbers didn't add up. The required surface area vastly exceeded what Hubble observed. You might be thinking, could Hubble have made a mistake? Could the July measurements have somehow missed the object's true size? That's a reasonable question, but the answer is almost certainly no. Hubble's instruments are calibrated to extraordinary precision. When it measures the brightness and apparent size of an object, it's accounting for distance, reflectivity, and phase angle. The margin for error isn't large enough to explain a 16-fold discrepancy. And remember, other ground-based telescopes corroborated Hubble's findings. Multiple independent observations converged on the same size estimate. So we're left with a mystery that refuses simple explanations. An object that appears to be 5.6 kilometers across is behaving as though it has the surface area of something 23 kilometers across. That's the central tension driving this entire investigation. Something about our understanding of 3I Atlas is incomplete. Either the object changed dramatically between July and November, or there's a mechanism at work that doesn't fit the standard Comet model, and the only way to figure out which explanation is correct is to follow the evidence wherever it leads. This isn't the first time astronomers have encountered an interstellar object that didn't behave as expected. You might remember Oumuamua, the first confirmed interstellar visitor discovered in 2017. That object displayed non-gravitational acceleration that couldn't be explained by conventional outgassing. The debate over Oumuamua's true nature continues to this day. But 3I Atlas is different. We have better data, more observations, higher resolution images, and most importantly, we have time. Unlike Oumuamua, which was discovered on its way out of the solar system, 3I Atlas is still within observational range. We can watch what happens next. We can test hypotheses in real time. The surface area problem is where the investigation begins, but it's not where it ends. Because once you start pulling on that thread, you realize there are other anomalies woven into the data. The jets themselves, for instance, don't behave quite like normal comet jets. Their structure, their velocity, their persistence, all of these factors add layers to the mystery. And when you start calculating the energy required to drive that mass loss, things get even more interesting. When astronomers analysed the November 8th and 9th images of 3I Atlas, they weren't just seeing generic comet tails. They were looking at a complex multi-directional jet structure that extended millions of kilometres into space. And the more closely they examined those jets, the more questions emerged about how they formed and what they tell us about the object itself. Let's start with the sheer scale. One set of jets extended approximately 1 million kilometres toward the Sun. That's roughly 2.5 times the distance between the Earth and the Moon. In the opposite direction, jets stretched about 3 million kilometres. These aren't small plumes. These are massive outflows of material travelling through space at velocities that had to be calculated based on how far they travelled and how long they'd been in motion. And that calculation revealed something unexpected. For a natural comet, the velocity of outflowing gas and dust is determined primarily by the thermal motion of sublimating molecules. When ice turns directly from solid to gas, a process called sublimation, the molecules escape the surface at speeds dictated by their temperature and mass. For carbon dioxide, which we know makes up the bulk of 3I Atlas's composition, the expected outflow velocity is around 0.4 kilometers per second. That number comes straight from the physics of gas dynamics. It's not a guess. It's based on the sound speed in CO2 gas at the temperatures you'd expect near perihelion. Now, if gas is leaving the surface at 0.4 kilometers per second, how long would it take to travel 1 million kilometers? You divide the distance by the velocity, and you get about 2.5 million seconds, which translates to roughly 29 days. For the 3 million kilometer jets, you're looking at nearly 3 months. That means the outgassing didn't just happen at perihelion on October 30th, it had to have been ongoing for weeks, possibly starting as early as late September or early October. The jets we're seeing in those November images represent material that was ejected over an extended period, gradually building up into the structures we observe today. But here's where it gets interesting. The solar wind, a constant stream of charged particles flowing outward from the Sun, acts as a brake on comet outflows. At some distance from the nucleus, the pressure from the solar wind becomes strong enough to halt the outward expansion of the comet's jets. For 3I Atlas, that stopping distance appears to be around 1 million kilometers. That tells us something important about the density of the material in those jets. Loeb calculated that in order for the solar wind to stop the jets at that distance, the mass density in the outflow must be on the order of millions of proton masses per cubic centimeter. That's a very specific, very measurable quantity, and it feeds directly into the next critical calculation. How much mass is 3I Atlas actually losing? When you multiply the mass density by the volume of the jets and factor in the velocity of the outflow, you arrive at a mass loss rate. For 3I Atlas, that rate comes out to roughly 5 billion tons per month. Let's put that number in perspective. Early observations of 3I Atlas's trajectory allowed astronomers to estimate its total mass based on gravitational dynamics. The best estimates suggest the object has a total mass of approximately 33 billion tons. If it's losing 5 billion tons per month, that represents a mass loss of about 15 to 16% of its total mass over the course of a single month. That's a staggering amount of material to lose in such a short time. Now you might be thinking, don't comets lose mass when they approach the Sun? Isn't that what comets do? Absolutely. Comets are defined by their volatile content. When they get close to the Sun, they heat up, their ices sublimate, and they develop the characteristic coma and tail that make them so visually stunning. But there's a limit to how much mass a comet can lose before it starts to fall apart. And more importantly, the rate of mass loss has to be consistent with the object's size and composition. For 3I Atlas, the mass loss rate observed in November is far higher than what you'd expect from an object of its measured dimensions. This is where the surface area problem comes roaring back into focus. The amount of mass being expelled is proportional to the surface area that's actively sublimating. If you have a small surface area, you can only lose so much mass per unit time, no matter how close you are to the Sun. But 3I Atlas is losing mass at a rate that would require a much larger surface area than what Hubble measured. The jets are the visible manifestation of that mass loss, and their structure tells us that something unusual is happening. The International Comet Quarterly Comet Observations Group, ICQ for short, has been tracking 3I Atlas closely. They've identified at least 7 distinct jets emanating from the object. 7. That's far more than you'd typically see from a single comet nucleus. Most comets display 2 or 3 active regions where jets originate, usually corresponding to areas where the surface composition or solar heating is particularly favourable for sublimation. But 7 jets suggest a much more complex surface structure, or possibly multiple active sources distributed across the object. Each of those jets has its own orientation and apparent brightness, which tells us something about the distribution of volatile materials on the surface. Some jets are more intense than others, suggesting uneven heating or compositional variations, and the fact that these jets persisted for weeks, rather than flaring up briefly at perihelion, indicates sustained outgassing activity over an extended period. That's not impossible for a natural comet, but it's unusual. It suggests that either the object has an extraordinarily high volatile content, or there's some mechanism enhancing the sublimation rate beyond what solar heating alone would produce. There's another detail that's easy to overlook, but critically important. The jets aren't symmetrical. They don't radiate evenly in all directions from a central point. Instead, they have a distinct directional structure, with more material flowing in certain directions than others. That asymmetry is what causes non-gravitational acceleration, a phenomenon where the act of outgassing creates a thrust that alters the object's trajectory. It's like a rocket engine, but instead of controlled combustion, it's the recoil from escaping gas. And 3I Atlas has displayed measurable non-gravitational acceleration during its approach to the Sun. That acceleration was detected in August, long before perihelion. It showed up as a small but persistent deviation from the purely gravitational trajectory that astronomers expected based on the object's mass and the Sun's gravity. At the time, that acceleration was modest, consistent with the relatively low mass loss rates observed by the James Webb Space Telescope in early August. But as 3I Atlas approached perihelion, the acceleration increased. The closer it got, the stronger the outgassing became, and the more pronounced the deviation from a purely ballistic trajectory. So now we have a picture of an object that's losing mass at an extraordinary rate, producing jets that extend millions of kilometers and exhibiting non-gravitational acceleration that's measurably altering its path through space. Each of these observations is consistent with a comet undergoing intense solar heating near perihelion. But when you add them all up and compare them to the object's measured size, the picture doesn't quite fit. The scale of the activity seems too large for the size of the object, and that brings us to the next critical question. Where is all that mass coming from? Let's talk numbers. Not vague estimates or hand-waving approximations, but actual calculated values based on the best data we have. Because this is where the mystery of 3i Atlas moves from. That's interesting to wait, that can't be right. Avi Loeb started with the density of the material in the jets. Based on where the solar wind stops the outflow, around 1 million kilometers from the nucleus, he calculated that the mass density in those jets is on the order of millions of proton masses per cubic centimeter. That's a precise measurement derived from the balance between outward gas pressure and inward solar wind pressure. It's not a guess, it's physics. Next, he calculated the volume of the jet structures. If a jet extends 1 million kilometers in radius, and we assume a roughly cylindrical or conical geometry, the total volume of material in the jets is enormous. Multiply that volume by the mass density, and you get the total mass contained in the jets themselves at any given moment. But that's not the full picture, because the jets are constantly being replenished. Material is continuously flowing out from the nucleus, replacing what's already moved farther out into space. To find the mass loss rate, you need to account for the velocity of the outflow. If material is moving at 0.4 kilometers per second, then every second, a new column of gas and dust is being added to the jet. Over the course of a month, roughly 2.6 million seconds, the cumulative mass loss adds up. When Loeb ran those numbers, he arrived at approximately 5 billion tons per month. That's billion with a B. To put it another way, that's about 2 million kilograms per second. Every single second, 3i Atlas is ejecting the equivalent of 20 fully loaded 747 aircraft worth of material into space. Now let's compare that to the object's total mass. Based on early trajectory measurements and gravitational dynamics, astronomers estimate that 3i Atlas has a total mass of around 33 billion tons. If it's losing 5 billion tons per month, that represents a mass loss of roughly 15 to 16% of its total mass in a single month. Think about that. In the span of 30 days, the object is shedding 1/6 of its entire mass. That's not a gentle sublimation process. That's a catastrophic rate of material loss. But here's the thing. Catastrophic doesn't mean impossible. Comets can and do lose significant fractions of their mass during close solar encounters. The question isn't whether a comet can lose that much mass. The question is whether a comet the size of 3i Atlas, with the surface area measured by Hubble, can physically sublimate enough material to account for the observed mass loss. And that's where the energy budget comes into play. When a comet loses mass, it's because solar radiation is heating the surface and causing volatiles to sublimate. The energy required to convert solid ice into gas is called the latent heat of sublimation, and it's a well-defined quantity for any given material. For carbon dioxide, which we know makes up about 87% of 3i Atlas, based on Webb's August 6th spectroscopic observations, the latent heat of sublimation is approximately 600 joules per gram. For water ice, it's much higher, around 2,835 joules per gram. So if we know the composition, we can calculate exactly how much energy is required to sublimate a given mass of material. Let's do the math. 5 billion tons is 5 trillion kilograms, or 5 quadrillion grams. Multiply that by 600 joules per gram, and you get 3 times 10 to the 18th power joules. That's the total energy required to sublimate 5 billion tons of CO2 over the course of 1 month. Now, that energy has to come from somewhere, and the only meaningful source is solar radiation. At perihelion on October 30th, 2025, when 3i Atlas reached its closest approach to the Sun, it experienced intense solar heating. At that range, the solar flux, the amount of solar energy hitting a given area per second, is significantly higher than what we experience on Earth. Specifically, it's about 700 watts per square meter. If you want to absorb 3 times 10 to the 18th joules over the course of a month, you need a certain minimum surface area to collect that energy. Loeb calculated that minimum area. It comes out to approximately 1,600 square kilometers. That's the radiating surface area required to absorb enough solar energy to sublimate 5 billion tons of CO2 in 1 month, assuming perfect efficiency and ignoring heat losses. Now, 1,600 square kilometers might sound abstract. So let's convert it into a more intuitive measure, the diameter of a sphere with that surface area. When you run the numbers, you get a diameter of roughly 23 kilometers. 23 kilometers. Remember that number. Now go back to July 21st, 2025, when the Hubble Space Telescope measured 3I Atlas. Hubble's photometric data indicated a maximum diameter of 5.6 kilometers, so we have a measured diameter of 5, 6 kilometers and a required diameter of 23 kilometers. The ratio between those two numbers is just over 4, but surface area scales with the square of the diameter, so a 4-fold difference in diameter translates to a 16-fold difference in surface area. In other words, 3I Atlas would need 16 times more surface area than it actually has in order to generate the observed mass loss through normal sublimation processes. That's the core impossibility. That's the mathematical contradiction that can't be swept under the rug or explained away with measurement uncertainty. The energy budget doesn't balance, the surface area isn't sufficient, and yet the mass loss is happening. The jets are real, the observations are verified, so something has to give. This is where Loeb said, and I quote, "Houston, we have a problem." He wasn't being flippant. He was acknowledging that the data is telling us something fundamentally inconsistent with the simple comet model. If 3I Atlas is a natural comet, and if the Hubble measurements are accurate, then the object shouldn't be able to produce the mass loss we're observing. The numbers simply don't work. Now there are a few possible explanations. One is that Hubble's measurements are wrong, which as we've discussed is highly unlikely given the precision of the instruments and the corroboration from ground-based observations. Another is that the composition isn't primarily CO2, and that there's some other more volatile material with a lower latent heat of sublimation that could account for higher mass loss rates. But Webb's spectroscopic data pretty clearly shows a CO2-dominated composition, so that avenue doesn't look promising either. The third possibility, and the one that Loeb and others are now seriously considering, is that 3I Atlas isn't behaving like a single, intact comet nucleus. What if the object broke apart? What if, sometime between the July Hubble observations and the November post-perihelion images, 3I Atlas fragmented into multiple pieces? If that happened, the total surface area would increase dramatically, even if the total mass remained the same. Imagine a single 5.6 kilometer sphere breaking into dozens or hundreds of smaller fragments. Each fragment has its own surface area, and when you add them all up, the total surface area could easily be 16 times larger than the original single body. That's a hypothesis we can test. Fragmentation would leave a visible signature in the observations. Instead of a single bright nucleus, we'd see multiple distinct points of light. Instead of a compact structure, we'd see a dispersed cloud or a string of fragments separated by measurable distances, and that's exactly what astronomers are looking for right now. Did 3I Atlas break apart near perihelion, or is it still intact, somehow producing mass loss at a rate that defies the conventional comet model? The answer to that question will determine which path this investigation takes next. Energy doesn't lie. It can't be created out of nothing, and it can't disappear into thin air. Every process in the universe, from nuclear fusion in the core of a star to the sublimation of ice on a comet, obeys the laws of thermodynamics, and when you apply those laws to the observations of 3I Atlas, you run into a problem that refuses to resolve itself through simple explanations. Let's revisit the energy calculation, but this time we'll dig deeper into what it actually means. When sunlight hits the surface of a comet, a portion of that energy is absorbed. How much gets absorbed depends on the albedo, the reflectivity of the surface. A darker surface absorbs more energy. A brighter, icier surface reflects more and absorbs less. For a typical comet composed of rock and ice, you might expect an albedo somewhere in the range of 0.04 to 0.10, meaning the surface absorbs 90 to 96% of the incoming sunlight. Let's assume a mid-range value and say that 3I Atlas absorbs about 90% of the solar radiation that hits it. During its closest approach to the Sun, based on Avi Loeb's calculations, the solar flux at perihelion was approximately 700 watts per square meter. If a surface area of 1 square meter absorbs 90% of that, it's taking in about 8,550 joules per second. Over the course of 1 month, roughly 2.6 million seconds, that single square meter absorbs about 22 billion joules. Now, how much energy does it take to sublimate 1 square meter's worth of CO2 ice? That depends on the thickness of the layer you're sublimating, but let's say we're dealing with a surface layer that's actively outgassing. The depth doesn't matter as much as the total mass loss rate, which we've already calculated. Here's the critical insight. If you need to sublimate 5 billion tons of CO2 in 1 month, and each ton requires 600 million joules of energy, you need a total of 3 times 10 to the 18th joules. Divide that total energy requirement by the amount of energy absorbed per square meter per month, 22 billion joules, and you get the required surface area, about 1,600 square kilometers. That's not an estimate. That's a direct calculation based on the energy balance between incoming solar radiation and the energy needed for sublimation. And once again, when you translate 1,600 square kilometers into the diameter of a sphere, you get roughly 23 kilometers. The math is inescapable. The observed mass loss demands a surface area that corresponds to an object much larger than the 5.6 kilometer diameter measured by Hubble. Now let's talk about what happens if the composition isn't pure CO2. Webb's August 6th spectroscopic observations showed that 3I Atlas is about 87% CO2, but that leaves 13% for other materials. Could that 13% be something with a much lower latent heat of sublimation? Something that could sublimate more easily and require less energy? The answer is, not really. The most common alternative volatiles in comets are water ice, methane and ammonia. Water has a much higher latent heat than CO2, so including water would make the energy problem worse, not better. Methane and ammonia have slightly lower latent heats, but not low enough to make a significant difference. And besides, Webb's data clearly shows CO2 as the dominant component. You can't just wish away the energy budget by assuming a different composition. Another factor to consider is heat conduction. When the surface of a comet is heated by the sun, that heat doesn't just sublimate surface ice. Some of it conducts into the interior, warming deeper layers. If the comet has a very low thermal conductivity, meaning heat doesn't penetrate very far, then most of the absorbed energy stays near the surface and drives rapid sublimation. On the other hand, if the thermal conductivity is higher, more heat gets carried into the interior and the surface sublimation rate is lower. But even if we assume the worst-case scenario for thermal conductivity, the numbers still don't add up. The surface area is simply too small to account for the observed mass loss. This is the point where Loeb's analysis shifts from "this is interesting" to "this fundamentally challenges the standard model." Because the energy budget isn't a minor discrepancy. It's not a factor of 2 or 3 that could be explained by measurement uncertainties or model assumptions. It's an order of magnitude problem. The object would need to be fundamentally larger, or there would need to be some additional energy source beyond solar heating, or the standard sublimation model would need to be completely revised. Let's consider the possibility of an additional energy source. Could there be internal heat driving the outgassing? Comets don't have internal heat sources like radioactive decay on a scale that would matter for sublimation. They're cold, inert bodies composed of ice and rock. The only meaningful source of heat is the sun. So unless there's some exotic process we're not aware of, and there's no evidence to suggest there is, we're stuck with solar heating as the primary energy input. That leaves us with 2 viable explanations. The first is fragmentation. If 3I Atlas broke apart into multiple pieces, the total surface area would increase dramatically, while the total mass remained roughly constant. Each fragment would have its own surface area, and collectively, they could provide the 1,600 square kilometers needed to account for the mass loss. The second explanation is more radical. If the object didn't fragment, and if it's still a single intact body, then it's not behaving like a natural comet. It's behaving like something else. That second possibility is where the investigation gets really interesting. Because if 3I Atlas maintained its structural integrity through perihelion, and is still a single body, then we have to ask, what mechanism could produce the observed mass loss without requiring an impossibly large surface area? One answer is a propulsion system, a thruster, a controlled release of material at much higher velocities than what you'd get from natural sublimation. Because if you increase the exhaust velocity, you can achieve the same thrust with much less mass loss. Think about it this way. A natural comet outgasses at about 0.4 kilometers per second, because that's the thermal velocity of CO2 molecules at the temperatures near perihelion. but a chemical rocket has exhaust velocities of 3 to 5 kilometers per second. An ion thruster can reach exhaust velocities of 10 to 50 kilometers per second or more. If you're using a high-efficiency propulsion system instead of passive sublimation, you can produce the same momentum transfer, the same thrust, with a fraction of the mass. And that means you don't need 16 times the surface area. You just need a more efficient way of expelling material. Now, I'm not saying that's what's happening. I'm saying that's one of the possibilities that the data forces us to consider, because the energy budget doesn't balance for a natural comet of the size we observed. Something has to explain the discrepancy. Either the object broke apart and increased its effective surface area, or it's using a mechanism that's more efficient than passive sublimation. Those are the two paths forward. And the only way to determine which one is correct is to look at the observations more closely and see if there's evidence of fragmentation. Which brings us to the next critical question. Did 3I Atlas actually break apart? Something happened to 3I Atlas between August and November. Something dramatic. And the key to understanding what that was lies in comparing the mass loss rates before and after perihelion. On August 6, 2025, the James Webb Space Telescope captured spectroscopic data of 3I Atlas. At that time, the object was still approaching the Sun, and its outgassing rate was relatively modest. Loeb and his colleagues analysed that data and calculated a mass loss rate of approximately 150 kilograms per second. That's not trivial. 150 kilograms per second is still a significant amount of material, but it's within the range of what you'd expect for a comet at that distance from the Sun. Now compare that to the November post-perihelion observations. Based on the jet structures visible in the images, the mass loss rate at or near perihelion is estimated to have been around 2 million kilograms per second. Let me say that again, 2 million kilograms per second. That's more than 13,000 times higher than the August rate. In scientific terms, that's an increase of 4 orders of magnitude. 4 orders of magnitude. That phrase gets used a lot in science, but it's worth pausing to appreciate what it actually means. An order of magnitude is a factor of 10. 4 orders of magnitude means a factor of 10,000. The mass loss rate didn't just increase. It didn't double or triple or even increase by a factor of 100. It increased by a factor of more than 10,000. That's not a gradual ramp up in activity. That's an explosive transformation. So what caused it? The answer, at least in part, is the inverse square law. As 3I Atlas moved closer to the Sun, the intensity of solar radiation hitting its surface increased dramatically. Solar flux follows an inverse square relationship with distance, meaning that if you halve your distance from the Sun, the intensity of sunlight increases by a factor of 4. As 3I Atlas moved closer to the Sun from its position in early August to perihelion on October 30th, the intensity of solar radiation increased dramatically. That change in distance alone accounts for roughly a factor of 5 to 6 increase in solar heating. But that's not nearly enough to explain a 10,000-fold increase in mass loss rate. Even accounting for the increased solar flux, you'd expect the mass loss rate to scale with the square or possibly the cube of the solar distance, depending on the specifics of the sublimation physics. But observations show something much more extreme. Loeb calculated that the mass loss rate follows a power law relationship with solar distance, with an exponent of about 10.5. That's an extraordinarily steep dependence. It means that small changes in distance result in enormous changes in mass loss rate. Why would that be? One possibility is that the surface composition or structure changes as the object heats up. Maybe at lower temperatures the surface is covered with a layer of refractory dust that insulates the underlying ice. But as the comet gets closer and the temperature rises, that dust layer is blown away or sublimated, exposing fresh ice beneath. Once the ice is exposed, outgassing accelerates rapidly, creating a runaway effect where more sublimation exposes even more ice, driving even more sublimation. That kind of feedback loop could explain the steep power law relationship, but it still doesn't solve the surface area problem. Even with a runaway sublimation process, you're still limited by the total amount of surface area available to radiate and absorb energy. And we keep coming back to the same fundamental issue. The observed mass loss rate requires a surface area that's 16 times larger than what Hubble measured. Multiple observers reported that 3I Atlas brightened dramatically near perihelion. Brightness is directly related to the amount of material in the coma, the cloud of gas and dust surrounding the nucleus. A brighter coma means more outgassing, which is consistent with the mass loss calculations. But brightness alone doesn't tell us whether the object fragmented. A single intact nucleus undergoing intense outgassing can produce a bright coma just as easily as a swarm of fragments. What we need is higher resolution imaging that can distinguish between a single compact nucleus and a dispersed cloud of fragments. That's the key diagnostic. If 3i Atlas broke apart, we should be able to see individual pieces separated by measurable distances. If it remained intact, we should see a single central condensation in the images, even if it's surrounded by a massive coma. The fragmentation hypothesis is appealing because it solves the surface area problem so neatly. Imagine that 3i Atlas broke into 16 roughly equal pieces. Each piece would have about 1/16 the volume of the original, which means each piece's radius would be about 40% of the original radius. But surface area scales with the square of the radius, so each piece would have about 16% of the original surface area. 16 fragments times 16% each equals a total surface area of about 2.5 times the original. Wait, that doesn't add up to 16 times larger. Let me recalculate. If the original object had a radius r and broke into 16 pieces, and if we assume those pieces are spherical, then each piece has a volume of 1/16 the original. Volume scales with the cube of radius, so each piece's radius is r divided by the cube root of 16, which is about r divided by 2.52. Surface area scales with the square of radius, so each piece has a surface area of roughly r divided by 2.52 squared times 4πr, compared to the original surface area of 4πr squared. When you add up 16 fragments, the total surface area is 16 times r divided by 2.52 squared, which works out to about 2.5 times the original surface area. That's not enough. To get a 16-fold increase in surface area, you'd need the object to break into hundreds or thousands of pieces, not just 16. And that's actually consistent with what happens during comet fragmentation events. Comets don't typically break into a handful of large pieces. They shatter into swarms of smaller fragments, ranging from meter-sized chunks to dust grains. If 3i Atlas underwent that kind of catastrophic disruption, it could easily produce the required increase in surface area. Loeb described the perihelion event as an explosion. That's a strong word, but it captures the essence of what the data suggests. At closest approach, something caused 3i Atlas to dramatically increase its mass loss rate in a way that can't be explained by solar heating alone, unless the effective surface area increased dramatically. The most straightforward explanation is that the object fragmented, breaking apart under tidal stress, thermal stress, or some other disruptive force. But here's the crucial question. Did it actually fragment? Or is the explosion just a metaphor for an intense outgassing event from an intact nucleus? The only way to know for sure is to look at the object directly and see whether it's one body or many. And that's exactly what upcoming observations are designed to determine. We've seen this before, not with an interstellar object but with a comet in our own solar system. And the comparison is instructive because it gives us a template for what fragmentation looks like and how it evolves over time. In July 1992, Comet Shoemaker-Levy 9 passed within 40,000 kilometers of Jupiter, well inside the planet's Roche limit. The Roche limit is the distance at which tidal forces from a massive body overcome the self-gravity of a smaller object, pulling it apart. For Shoemaker-Levy 9, crossing that threshold was catastrophic. The comet shattered into at least 21 distinct fragments, each one following a slightly different trajectory, but all of them bound gravitationally to Jupiter. Over the next 2 years, astronomers watched as those fragments gradually separated. Tidal forces don't just break an object apart instantaneously. They also create a differential velocity between the fragments, causing them to drift away from each other over time. By the time Shoemaker-Levy 9 impacted Jupiter in July 1994, the fragments were strung out in a string of pearls configuration, spread over several 100,000 kilometers along the comet's orbital path. That image, the string of pearls, became iconic. It's what fragmentation looks like when you observe it from a distance. Not a chaotic explosion, but an orderly procession of separate bodies, each one visible as a distinct point of light in telescopic images. Now, 3i Atlas didn't pass close to Jupiter, it passed close to the Sun. But the same physical principles apply. Tidal forces near the Sun can be just as disruptive as tidal forces near Jupiter, depending on the object's structure and composition. If 3i Atlas is a loosely bound rubble pile, a collection of ice and rock held together by weak gravitational and cohesive forces, then the tidal stress at perihelion could have been enough to pull it apart. Avi Loeb predicted this possibility back in October 2025, a month before perihelion. He wrote that if 3I Atlas has low tensile strength, it could fragment during its closest approach to the Sun. That wasn't a wild guess. It was a calculated prediction based on the object's orbital parameters, its estimated density, and the known tidal stress at perihelion. He even cited the Shoemaker-Levy 9 precedent as a reference point. So the question isn't whether fragmentation is possible. It clearly is. The question is whether it actually happened. And if it did, we should see the same kind of signature that we saw with Shoemaker-Levy 9. Multiple distinct fragments separated by measurable distances, gradually drifting apart under the influence of tidal forces and differential velocities. The key observational test is time. If 3I Atlas fragmented at perihelion on October 30th, and if the fragments are drifting apart at even modest velocities, say a few meters per second, then by mid-December they should be separated by tens of thousands of kilometers. That's large enough to resolve with high-resolution telescopes. Hubble should be able to see individual fragments if they exist. Ground-based adaptive optics systems should be able to distinguish a string of pearls from a single compact nucleus. But here's the catch. If the fragmentation produced a cloud of small pieces rather than a few large chunks, the individual fragments might be too small and too numerous to resolve clearly. Instead of seeing distinct points of light, we'd see a diffuse, elongated coma with no obvious central condensation. That would still be evidence of fragmentation, but it would be less definitive than seeing separated nuclei. There's another factor to consider. Tidal forces don't just pull an object apart, they also induce rotation. When a body experiences differential tidal stress, stronger on one side than the other, it starts to spin. That spin can compound the disruptive effect, especially if the object was already rotating before perihelion. A rapidly spinning, loosely bound rubble pile is much more susceptible to fragmentation than a solid, non-rotating nucleus. We don't have direct measurements of 3I Atlas's rotation rate before perihelion, but we can infer something about its spin from the asymmetry of the jets. Jets that are oriented in specific directions suggest localized outgassing from active regions on the surface. If the object is rotating, those active regions sweep around, creating a spiral pattern in the coma. Some observers have noted possible spiral structures in images of 3I Atlas, which would be consistent with rotation. But without time-resolved photometry, it's hard to pin down the exact rotation period. If fragmentation occurred, the next few weeks will tell the story. Tidal forces near the Sun would have imparted a velocity dispersion to the fragments, causing them to separate over time. The farther the fragments get from perihelion, the weaker the Sun's gravity becomes, and the more the fragments' trajectories diverge. By the time 3I Atlas reaches its closest approach to Earth on December 19th, the fragments should be well separated if they exist. That December 19th observation is crucial. Not only is it the optimal viewing opportunity from Earth, but it's also the moment when we'll have the best angular resolution to distinguish between a single intact nucleus and multiple fragments. If telescopes show a single bright point of light with no sign of separation, that would strongly suggest the object remained intact. If they show a dispersed cloud or a linear chain of fragments, that would confirm fragmentation. And here's the thing. The fragmentation hypothesis is testable. It makes specific predictions about what we should see in December. Either the predictions are confirmed or they're not. There's no ambiguity. That's the beauty of science. We're not guessing. We're making observations and checking them against predictions. And within a matter of weeks, we'll know which scenario is correct. But what if the December observations show an intact nucleus? What if 3I Atlas didn't fragment? Then we're back to the surface area problem, and we're forced to consider the alternative explanation. Mark your calendar. December 19th, 2025. That's the date when 3I Atlas makes its closest approach to Earth, passing at a distance of approximately 269 million kilometers. That might sound far away, and it is by everyday standards. But in astronomical terms, it's close enough for high-resolution observations that will finally answer the central question. Is 3I Atlas a single intact object, or did it break apart near perihelion? Let's put that distance in perspective. At 269 million kilometers, 3I Atlas will be roughly 1.8 times the distance from the Earth to the Sun. Compare that to the extent of the jet structures, which reach out about 3 million kilometers from the nucleus. That means the jets themselves subtend an angular size on the sky that's large enough to be resolved by ground-based telescopes with adaptive optics, and certainly by space-based observatories like Hubble and Webb. This is a rare opportunity. Interstellar objects don't pass through the inner solar system very often, and when they do, we usually don't get a second chance to observe them in detail. Oumuamua was discovered on its way out, and by the time astronomers realized what they were looking at, it was already too faint to study in depth. 2I/Borisov, the second confirmed interstellar comet, was observed extensively during its passage, but it never came as close to Earth as 3I Atlas will on December 19th. This is, quite literally, a once-in-a-lifetime viewing opportunity for this particular object. Multiple observatories are preparing to point their instruments at 3I Atlas during the closest approach. Ground-based telescopes around the world will track the object continuously, capturing images and spectra at the highest possible resolution. The Hubble Space Telescope, which provided the original size measurements in July, will be trained on 3I Atlas again to see whether the object's appearance has changed. If fragmentation occurred, Hubble should be able to resolve individual fragments separated by tens of thousands of kilometers. If the object remained intact, Hubble will see a single compact nucleus, possibly surrounded by a bright coma. The James Webb Space Telescope will also be observing, though its primary contribution will be spectroscopic rather than imaging. Webb's infrared spectrographs can detect subtle changes in composition and temperature that might reveal details about the physical state of the object. If there are multiple fragments with different temperatures or compositions, Webb might be able to distinguish them, even if they're too close together to resolve spatially. But the December 19th opportunity isn't just about professional observatories. Amateur astronomers with moderately sized telescopes will also be able to track 3I Atlas. The object's brightness has varied significantly over the past few months, and if it's still actively outgassing, it should be visible to backyard telescopes in the 10 to 12-inch range, assuming dark skies and good seeing conditions. That means there's a real possibility of distributed observations from around the globe, with multiple independent observers capturing data that can be cross-checked and compiled. There's another asset in play that's worth mentioning: the European Space Agency's JUICE spacecraft, short for Jupiter Icy Moons Explorer, launched in 2023 and is currently on its way to Jupiter. While its primary mission is to study Jupiter's moons, it's equipped with high-resolution cameras and spectrometers that can also observe other objects in the solar system. JUICE is currently in a unique position along its trajectory, and there's been discussion within the scientific community about whether it could contribute observations of 3I Atlas from a different vantage point. Multi-point observations from both Earth and JUICE would provide parallax measurements that could help pin down the three-dimensional structure of the jet systems and any potential fragmentation. The diagnostic power of these observations can't be overstated. If 3I Atlas fragmented, the signature will be unmistakable. We'll see either a string of distinct fragments or a highly elongated diffuse structure consistent with a cloud of smaller pieces. If the object remained intact, we'll see a compact point-like nucleus with symmetric or asymmetric jets radiating outward. There's no middle ground. The observations will decisively distinguish between the two scenarios, but there's another layer to this. Even if the December 19th observations confirm fragmentation, we'll still want to understand why it happened. Was it purely tidal disruption? Was it thermal stress from solar heating causing internal pressure to build up until the object burst? Was there some pre-existing structural weakness that made the comet more susceptible to breakup? Those questions can be addressed by analysing the distribution and properties of the fragments. If we see a handful of large fragments of roughly equal size, that would suggest a relatively orderly breakup, possibly along pre-existing fracture lines. If we see a large number of small fragments with a wide range of sizes, that would suggest a more violent explosive event. The mass distribution of the fragments, estimated from their individual brightnesses, would also provide clues about the internal structure of the original object. And then there's the trajectory. Each fragment, if they exist, will follow a slightly different path. Tidal forces during the breakup would have imparted small velocity differences between the fragments, causing them to drift apart over time. By tracking those trajectories and working backward, we can reconstruct the exact moment and location of the fragmentation event. That, in turn, tells us something about the forces involved and the structural properties of the original comet. All of this data will be available by late December or early January, The observations happen on December 19th, but it takes time to process and analyse the data, especially spectroscopic data from Webb. By February 2026, we should have a comprehensive picture of what 3i Atlas looked like during its closest approach to Earth, and by extension, what happened to it at perihelion. But here's the thing. All of that assumes we'll find evidence of fragmentation. What if we don't? What if the December 19th observations show a single intact nucleus with no sign of breakup? What if the surface area problem remains unsolved even after we've looked for fragmentation and found none? Then we're forced to confront the alternative explanation. And that's where the investigation takes a turn into territory that makes a lot of scientists uncomfortable. Not because the evidence isn't there, but because the implications are profound. If 3i Atlas didn't fragment, and if it's still producing the observed mass loss from a surface area that's too small to account for it through natural sublimation, then we have to ask, what else could explain the observations? Let's be clear about what we're discussing here. This isn't speculation for the sake of sensationalism. This is a logical consequence of following the data wherever it leads. If the December observations show that 3i Atlas remained intact, if there's no fragmentation to explain the increased surface area, then we're left with a simple fact. The object is expelling material at a rate that can't be accounted for by passive sublimation from a 5.6 kilometer nucleus. So what are the alternatives? One possibility is that the outflow velocity is higher than the 0.4 kilometers per second we'd expect from natural comet outgassing. Remember, mass loss rate isn't just about the total amount of material expelled, it's also about how fast that material is moving. If the exhaust velocity is higher, you can achieve the same momentum transfer, the same thrust, with less mass. Think about propulsion systems. A chemical rocket expels combustion products at velocities of 3 to 5 kilometers per second. That's roughly 10 times faster than comet outgassing. An ion thruster, which uses electric fields to accelerate charged particles, can reach exhaust velocities of 10 to 50 kilometers per second or even higher. That's 2 orders of magnitude faster than natural sublimation, and the advantage of higher exhaust velocity is efficiency. You get more thrust per unit of expelled mass. Now, I'm not saying 3i Atlas has a rocket engine. I'm saying that if it's behaving like a propulsion system rather than a passive sublimating comet, then the mass loss calculations change dramatically. Instead of requiring 16 times the surface area, you might only need the observed surface area if the material is being expelled at higher velocities. And that's testable. Spectroscopic observations can measure the velocity of the outflowing gas by looking at the Doppler shift of emission lines. If the gas is moving significantly faster than 0.4 kilometers per second, that would be evidence of a non-sublimation mechanism. The upcoming observations in December will provide exactly that kind of data. Webb spectrographs can measure the line-of-sight velocity of the gas in the jets with high precision. If the measurements come back showing velocities of 1, 5, or 10 kilometers per second, that would be a game-changer. It would mean the outflow isn't just passive sublimation, it's something more energetic, more controlled. There's another piece of evidence that's worth revisiting, the non-gravitational acceleration. As I mentioned earlier, 3i Atlas has been displaying measurable deviations from a purely gravitational trajectory. That acceleration was detected in August and has continued through perihelion. For a natural comet, non-gravitational acceleration is expected. It's caused by the recoil force from outgassing, which acts like a tiny rocket thrust. The magnitude of the acceleration depends on the mass loss rate and the direction of the jets. But here's the interesting part. The non-gravitational acceleration of 3i Atlas is aligned almost exactly along its direction of travel. That's unusual. For most comets, the acceleration has a component that's perpendicular to the trajectory, because the jets aren't perfectly aligned with the comet's motion. But if the jets are deliberately oriented to produce thrust in a specific direction, then the acceleration would be much more aligned with the velocity vector. And that's what we see with 3i Atlas. Loeb and others have calculated the statistical likelihood of this alignment occurring by chance. The answer, very low. If you assume the jets are randomly oriented, the probability of them producing an acceleration that's aligned within a few degrees of the trajectory is less than a few percent. That doesn't prove intentional control, but it does suggest that whatever mechanism is driving the outgassing, it's not entirely random. Then there's the orbital alignment itself. 3. The Atlas is travelling on a retrograde trajectory, meaning it's moving opposite to the direction that most objects in the solar system orbit the Sun. That's not uncommon for interstellar objects. They can come from any direction. But what is unusual is that the trajectory is aligned within about 5 degrees of the ecliptic plane. The ecliptic is the plane in which Earth and most of the planets orbit, and it represents a kind of preferred direction in the solar system. For a randomly oriented interstellar object, the probability of having an orbital inclination close to the ecliptic is quite low, about 0.2%, or 1 in 500, and there's the size issue. Compared to Oumuamua, 3I Atlas is about 1 million times more massive. That's an enormous difference. Oumuamua was estimated to be around 100 to 200 meters in its longest dimension, with a mass of maybe a few million kilograms. 3I Atlas, on the other hand, has a mass on the order of 30 billion tons. Finding 2 interstellar objects in the span of 8 years, with such a dramatic difference in size, raises questions about the underlying population. How common are interstellar objects of this size? What does the size distribution look like? And are we just exceptionally lucky to have detected 2 of them in such a short time? When you combine all these factors, the mass anomaly, the orbital alignment, the size difference, the aligned non-gravitational acceleration, you get a cumulative statistical improbability. Loeb has estimated that the combined likelihood of all these factors occurring by chance for a natural astrophysical object is roughly 1 in 100 million. That's 0.00001%. Now, rare things do happen. Improbable events occur all the time if you wait long enough. But when multiple independent improbabilities stack up, you have to at least consider the possibility that there's an underlying reason they're all present in the same object. The alternative hypothesis, and this is the part that makes headlines and generates controversy, is that 3I Atlas might be a technological object. Not a spaceship in the science fiction sense, but an artifact of some kind. A probe, a piece of equipment, something that was constructed rather than formed through natural astrophysical processes. If that's the case, then the observed behavior makes a lot more sense. A propulsion system could explain the high exhaust velocity. Deliberate trajectory adjustments could explain the aligned non-gravitational acceleration. And an engineered structure could have material properties that differ from natural comets, affecting how it responds to solar heating. Now, I want to be very careful here. The technological hypothesis is speculative. It's a possibility that emerges from the data, but it's not the only possibility, and it's certainly not proven. The fragmentation hypothesis remains viable until we have observations that rule it out. And even if fragmentation is ruled out, there could be natural explanations we haven't thought of yet. The universe is full of surprises, and nature has a way of producing phenomena that look artificial until we understand the underlying physics. But the point is this: if the December observations show an intact object with no fragmentation, and if the spectroscopic data show high exhaust velocities, and if the trajectory continues to display aligned non-gravitational acceleration, then the technological hypothesis becomes harder to dismiss. Not because we want it to be true, but because the alternatives require increasingly contrived explanations. Avi Loeb has been very explicit about this. He's not claiming that 3I Atlas is an alien spacecraft. He's saying that the data raises questions that deserve serious scientific investigation. And the way to investigate those questions is to gather more data, test specific predictions, and follow the evidence wherever it leads. That's what science is supposed to do. Not shy away from uncomfortable possibilities, but embrace them as opportunities to learn something new about the universe. The phrase Loeb uses is "stay curious," and that's exactly the right approach. Curiosity doesn't mean credulity. It doesn't mean accepting wild claims without evidence. It means being open to possibilities, testing them rigorously, and adjusting your beliefs based on what the data actually shows. And right now, the data is showing us something we didn't expect. Whether that something is a natural comet that fragmented in an unusual way, or whether it's something more exotic remains to be seen. So here we are. Millions of kilometers from Earth, an object of interstellar origin is hurtling through space, leaving a trail of evidence that challenges our understanding, and in just a few weeks, we'll have the opportunity to observe it in unprecedented detail. The data that comes back from those December observations will determine which direction this investigation goes. Will we confirm fragmentation and close the case on 3I Atlas as an unusually active but ultimately natural comet? Or will we find an intact object that forces us to reconsider what we're looking at? Let's summarize the 2 competing hypotheses. The first is the fragmentation scenario. In this picture, 3I Atlas was indeed a single intact comet when Hubble observed it in July. But as it approached perihelion, and experienced intense solar heating and tidal stress, it broke apart into dozens or hundreds of smaller fragments. The total surface area of all those fragments combined is much larger than the original single nucleus, which explains the high mass loss rate observed in November. The jets are the result of intense outgassing from multiple active fragments, each one sublimating independently. Over the coming weeks, those fragments will continue to separate under the influence of differential velocities, and by December 19th, they should be clearly resolved as distinct objects or as a dispersed cloud. The second hypothesis is that 3I Atlas remained intact. In this scenario, the object did not fragment at perihelion. It's still a single body, but it's expelling material at a rate and velocity that can't be explained by passive sublimation alone. The high mass loss rate is achieved not by increasing surface area, but by increasing exhaust velocity. This could be the result of a natural process we don't fully understand, perhaps some kind of internal pressure build-up that causes explosive outbursts, or it could be evidence of a propulsion system. In either case, the object's behavior deviates significantly from what we expect for a typical comet. The December 19th observations will distinguish between these scenarios. High-resolution imaging from Hubble, combined with spectroscopic data from Webb, will tell us whether we're looking at one object or many. Velocity measurements of the jets will tell us whether the outflow is consistent with natural sublimation or whether it's moving faster than expected. Trajectory tracking will tell us whether the non-gravitational acceleration remains aligned with the object's motion or whether it changes direction in a way that suggests structural changes. But December 19th isn't the end of the story. It's just one data point. Even after the closest approach, 3I Atlas will continue to be observable for weeks or even months as it moves away from the Sun and back out into interstellar space. Extended observations will allow us to track how the object's activity evolves over time. Does the outgassing diminish as it moves farther from the Sun, as we'd expect for a natural comet? Or does it remain constant, suggesting an internal power source? Those long-term trends will provide additional constraints on the possible explanations. The data analysis itself will take time. Raw images and spectra need to be processed, calibrated, and interpreted. That work will likely extend into January and February 2026. Once the results are compiled, they'll be submitted for peer review and eventually published in scientific journals. That's the standard process, and it's important because it ensures that the conclusions are vetted by the broader scientific community. But here's the thing. We don't have to wait for formal publication to start drawing conclusions. As soon as the preliminary data comes back, astronomers will be sharing their findings through informal channels, conference talks, preprint servers, social media, and yes, platforms like this one. The scientific conversation happens in real time now, and anyone who's interested can follow along. You don't need a PhD to understand the basic questions being asked or the methods being used to answer them, and that's what makes this moment so exciting. We're not reading about a discovery that happened decades ago and was quietly resolved in some dusty journal article. We're witnessing a live investigation. The observations are happening right now, the data is being collected as we speak, and in a matter of weeks we'll have answers, or at least we'll have new questions that are more precise and better informed than the ones we're asking today. What should you be watching for? First, look for announcements from major observatories about their December observations. Hubble and Webb both have public outreach programs that share images and results as they become available. Second, follow the work of astronomers like Avi Loeb, who are actively analysing the data and publishing their findings. Third, keep an eye on amateur astronomy communities, where independent observers are tracking 3I Atlas and sharing their own images and measurements. And if you have access to a telescope, consider trying to observe 3I Atlas yourself. It won't be easy, the object is faint, and you'll need to know exactly where to look, but it's not impossible. There are ephemeris tables available online that give the precise coordinates of 3I Atlas on any given date. With a bit of patience and a dark sky, you might be able to capture your own piece of this historic observation. Regardless of what the December data shows, this investigation has already taught us something valuable. It's reminded us that the universe is full of surprises, and that our models and assumptions are always provisional, always subject to revision in light of new evidence. That's not a weakness of science, that's its strength. Science doesn't claim to have all the answers, it claims to have a process for finding answers, and that process works precisely because it's self-correcting. So stay curious, stay engaged, follow the observations, read the papers, ask questions, And most importantly, resist the temptation to draw conclusions before the data is in. Whether 3i Atlas turns out to be a fragmented comet or something more unusual, the journey toward understanding it is what matters. Because that journey, the process of gathering evidence, testing hypotheses, and refining our understanding, is science at its best. And we're all invited to be part of it.